наш семинар. Вот. Ну, ага. Good afternoon, everybody. Our today's speaker is Ivan Kаспирович from the Ruden University, and Ivan will talk about some applications of, I don't know how to pronounce correctly, Baumgart stabilization method.
Yeah, Baumgart, he's a German.
Please, you can start your presentation.
Yeah, I think he's from either from Switzerland or from German, but the correct pronunciation is Baumgart, but in Russian literature, sometimes we refer as just Baumgart due to the Russian ear. Okay, so I think I will commence now. So thank you, greetings everyone, and thank you for having me, because it's a really pleasure to have this report at this seminar. So today I'm going to talk about some applications of, as you have announced already, Baumgart stabilization method. So the idea is basically the behavior of dynamical systems can be described with the help of ordinary differential equations, right? So Lagrangian equations, Hamiltonian equations, and even the Jacobi-Hamilton equations are in partial derivatives, but still the result will be in differential equations. So, but we do know that only few systems that are studied in law courses can be solved analytically. So only for few systems we can find an analytical solutions. Just for example, the problem of two bodies, right? We do know the analytical solution. It's already known. So for all other systems, we have to use some of the methods. So the main idea is we can actually use differential finite differences scheme or numerical integrations to solve these problems. So, but however, when numerically integrated systems of motions with mechanical constraints, the effect of accumulations of rounding errors or other errors can lead to the instability of the system. So in other words, if we have a finite difference scheme, so it's an infinitely, not infinitely, but a lot of repeats of this scheme, and at each step, the accumulation of error occurs, right? So, and this accumulation can lead to the instability. And the idea of Baumgart stabilization method is to get rid of it. And so, to limit the magnitude of such accumulation, Joachim Baumgart proposed an algorithm to stabilize the constraints during the numerical integration. And this work was basically the work of Baumgart, was also researched by the former Department of Theoretical Mechanics of our institute, and first with the lead of Galiulin, Lihaksfilovich, and then with the lead of Mukhalyamov, who is present here. So he's my scientific supervisor, and we do work in this area. So that's my introduction, and I think let's start. So the main goals of the research is, first of all, to estimate some kinds of stabilization function such that this function will guarantee a stable numerical solution. So in other words, not all functions can guarantee the stable numerical solution, but we have to find one. So the other goal is to implement this to some other areas in dynamical problem. For example, we want to implement it to solve the inverse dynamical problem, to solve the optimization problem, and so on. So, and the other goal is to make a modification of this method. So Robert Gregorevich and me, we have already worked on such modifications, and I am about to introduce them to you in this report. Okay, so let's continue. Well, the problem statement, short introduction, quick summary. So we actually do know that all systems can be described with the help of the generalized coordinates is a vector Q, and it's a set of coordinates, right? Q sub Qn, and so on, Q1, Qn, and so on. And so in mechanics, we use dot to denote a full-time derivative. So that's basically the generalized velocity. It can be technically everything. It can be momentum. It can be just geometrical coordinates. Doesn't matter. So that's the big idea behind the analytical mechanics. So generalized coordinates can technically describe anything. Okay, so, and as I have said, that to describe systems, we should have used some equations, right? So we should introduce some equations. For example, you all know that in analytical mechanics, first we introduce the Euler-Lagrange equation. That's Euler-Lagrange equation. And then the next step is to introduce the Hamilton canonical equations in canonical form. It's basically with a simplex structure, but with the Poisson brackets. That's not the main idea of the conversation. Okay, so the idea is technically they all are differential equations, right? And we have to apply the theory to get some data from these numerical equations. It will be ideal if we will get a solution, right? But sometimes we can't. And in order to do this, to get a solution, we have to use the Baumgarten stabilization method. Okay, so, and nevertheless, we want to introduce, and if have in our mechanical system a set of constraints, mechanical constraints, the restrictions on these variables, on q and generalized q dot, generalized velocity. So these are the set of mechanical constraints. They can be either holonomic or non-holonomic. So holonomic are technically the restrictions between the coordinates and the velocities, and only if the restriction is kinematic and integrable, right? So if kinematic constraints cannot be reduced to the integrable form, then it's not holonomic. So I will be talking about either of these. Okay, so let's continue. Well, how to solve mechanical problems with the constraints? So from calculus, you do know that if you want to find the extrema, you have to introduce Lagrange multipliers. So these are the vector lambda is the set of Lagrange multipliers. And so that's technically I have expanded the formula for the Lagrange equation of the Euler-Lagrange equation of the second kind, but only with constraints, right? The set of constraints. So this is our system. Let's suppose that they are holonomic. Then I'll move to non-holonomic. Okay, so this is our system, and what we want, how to solve it. So technically, what we need to do is to take the second derivative, right? Because when we take the second derivative, here we will get inevitably something like that. Double dot, something like that. I think it was something like that. I think it was the first derivative. So times q double dot I. And this system can be treated as a linear algebraic equation with respect to the generalized accelerations and Lagrange multipliers. And so we can find the solution to this system, and only then we can start integrate it. So such systems can be called differential algebraic equations, because first we have to find the solution to the system of algebraic equations with respect to generalized accelerations and Lagrange multipliers. Okay, but so that's what I have to write. I forgot that. So I couldn't write it. Okay, so well, so that's that formula, and it's the set of differential algebraic equations. But the zero actually is a problem, because it means that it remains the same, right? But if we have, for example, in numerical integration, the rounding errors, so it might not be zero, right? It might not be perfect. So we have to introduce another force then I'll show that this force must have a dissipative nature. So this force will reduce the deviation from this constraint. And Baumgarten first suggests that instead of 0, we have to put here a linear form, an arbitrary linear form of the derivative of the constraints and the constraints themselves, right? So that's where the coefficients are chosen. So you will get a stable numerical solution. So you arbitrarily pick this coefficients, this matrix, basically a matrix, right? A components of a matrix. And so you do get a stable solution for these differential algebraic equation. So, but it doesn't change the mechanics, because technically all the constraints are equal to 0, right? It's 0. It's also 0, right? It's the constraint. So technically it does not change the properties of the mechanics. So it's just a trick to remove the instability. And so this form was suggested by Joachim Baumgarten, I think in 1960s, 70s. But the generalized version, the modified version, was researched, was investigated by the Department of Theoretical Mechanics, by Galiulin, and then by Mukharlamov, Garavshich, and by me. So that's...
Yes,
yeah.
Excuse me, Ivan, if I can ask a question. So you say that if you add this right-hand side different from 0, then the solution becomes stable. Why it is like that? Why it becomes stable if you introduce this additional term in the equation?
Okay, so well, it happens because I can show you later that by manipulating the magnitudes of the values of these coefficients. So so first of all, if, for example, I will show you that if it was something like that, then the idea is the solution to this is actually G is equal to, I don't know, a t squared. No, a t plus b, right? So that's the solution. And if, for example, you get something like that, ag is equal to ag prime plus bg. So this, if I'll draw the picture, so we have g and y-axis and t and x-axis, it can increase, right? So, but this, if I'll choose the coefficients a and b such that the trivial solution will be asymptotically stable, it can be something like this. And so that's the idea. And nevertheless, I can then show the estimations that proves that the magnitudes, the values of these components, they affect on the increasing of this accumulation. So this fact does change so these values, they do affect on the accumulation of errors. So that's the briefly a short explanation.
Well, yes, but it accumulates, but why it acts on this accumulation, but why it acts in the direction of its stability, but not instability? This is what not exactly clear for me.
Well, when I was talking about instability, the instability in order to for numerical solution, right? So well,
by instability of numerical solution, you understand that there is no convergence in some sense of what? Could you please explain what you understand by the instability of the numerical solution?
So the instability with respect to constraints, well, by the instability with respect to constraints, I mean that, for example, the deviations from the constraint equations, for example, if I denote y as a deviation from the constraint equation, and in time, this deviation will increase. So that's what I assume by the instability, right?
So you compare the exact solution and numerical solution, and numerical solution deviates from the exact solution.
That's correct.
The difference grows in time. The difference grows in time. Okay, thank you for this.
Okay, so and this generalized function
this question is not exactly clear. Yeah.
What?
Well, please continue.
Oh, okay. So, and this function is investigated by Kaspировich and me. Okay, so I'll continue. And so this function obviously should be chosen such that, of course, if the constraint is equal to 0, then this function must be equal to 0, right, by definition. And as I have wrote here, the trivial solution must be stable. So the value of g, the deviation from the constraints, shall not increase. Okay, so now let's move to the non-holonomic constraints, and this form of non-holonomic constraints. We assume that this differential form, the coefficients of this differential form are not integrable. So if I'll introduce the non-holonomicity tensor, not all of them will be equal to 0. Some of them will not be equal to 0, which means that these constraints cannot be never represented in the form of the integrable kinematic constraint. So that's what I assume by non-holonomic constraints. So there are two actually approaches to solve this problem. First is the Lagrange multipliers approach. It's just basically the same thing. Basically the same thing, but instead we had termed there g mu, the partial derivative of the constraint with respect to the coordinates, but here we'll have the respect to the second derivative. So, but you'll have the same reactance force, the same reaction force, and the algorithm is the same. So, and the dynamical equations, they will include the stabilization terms. But another approach was investigated by Chapligin, Voronets, Appel, Maggi, and so on, and they actually modify the Lagrange equations so that some of them the structure of equations will inevitably include the constraints themselves. So in this case, we consider stabilization after solving for example, Chapligin or Voronets equations. So I'll explain it. Well, for example, I'll consider Chapligin's approach. In this approach, Chapligin is a famous Russian mathematician in the beginning of the century, beginning at the end of the century, sure. Okay, so he suggested that these kinematic constraints, non-holonomic constraints, can be treated as follows. So we can, if this constraint is chosen in the specific form, and in this form, the generalized velocities or coordinates can be chosen. So one set of them will be a function of another. So in other words, we'll call this set dependent and this set an independent, right? It's connected with actually non-holonomicity tensor, right? So if it's 0, then this term is 0. Okay, so, and this is our constraints, and I'll introduce stabilization after the equations, the stabilization only for dependent variables, as you can see here. So f here is the stabilization function. It can be also chosen according to those conditions, right? So the symptotic solution should be stable. So these are two approaches to solve the stabilization problem for the non-holonomic constraints. Okay, so let's continue. And the short example that was considered, I think it's name for 5 book, the sliding sledge. the sliding sledge. It was considered, I think, by Chaplygin. It can be called in foreign literature as a Chaplygin sledge. So that's the Lagrange equation, and it's the sledge. It's basically a sharp wheel, and you can see that this wheel, it has a center, and A is the distance between the touching of the surface and the center of mass of this wheel. So we have the coordinates x and y of this wheel and the angle between the chosen axis, theta. Well, let's choose, I don't know, it can be anything, so we choose between the x-axis, for example, doesn't matter. So that's the Lagrange function for this Chaplygin sledge. And the non-Coulombic constraint appears here with a condition that actually this wheel cannot move along this eta line. So it cannot move perpendicular to its motion, right? So it should be always along this motion, along the velocity. So that's, by the way, that's our constraint, right? We have said that y prime over x prime should be always at this angle, theta. And so these are two approaches, the Lagrange multipliers and the Chaplygin equations. In this case, I have already derived the formula, showed you the final formula. Here, k is the stabilization term. Stabilization equation I have chosen its simplest way. So if h, I'll denote our holonomic constraints, something like this. So k is just the coefficient between h prime and kh. And so we choose k, so the numerical solution should be stable. And k also appear in this approach, in this equation, right? So when I take the first derivative, I'll equate it to the coefficient of the constraint itself. And the results of the numerical integration are presented on the graphs. So the first is coordinate x, angle, theta, and coordinate y. So this is basically the same line, but you can see that I think if it will keep going, then the deviation, the difference will inevitably grow, and it depends on the value of k. And we actually made a model. It's pretty simple problem. So the model, that's the model of the sledge. Turn it on. Let me turn it on. Okay. So you can see that it turns out, right, and it will slide down forever. Okay, so technically the trajectory can be anything based on their initial conditions, obviously. But the main idea that the stabilization allows us, no, it doesn't matter what equations do we choose, we can still get a stable numerical solution. Okay, so well, and now I'll move to the part why. Why does it happen? Why do these terms, the stabilization terms, allow us to achieve the stable numerical solution? And if I'll write, for example, for holonomic equation, I can do any this thing for non-holonomic. It will not vary rapidly, so it doesn't matter. So here I denote the stabilization equation as follows. So here k is a constant matrix with the coefficients, and this matrix can be called the matrix of perturbation parameters. So these components can be a function of time, they can be just constant values. So in this approach, I just we just consider them as constant values. So to make the estimation of what these values should actually equal to. Okay, let's, for example, choose the simplest finite difference scheme, the Euler method of the first order. So we have this are dynamic part and this are kinematic part, and then we introduce the deviations from the constraint. It's actually a tensor sum of these deviations. So I remind you that these are our harmonic constraints, and these are the first derivative of the constraints. And so I want to state this condition. So here in the indexes in brackets represents the number of steps at the numerical integration, and y sub k is just the component of that vector y. And so I want that the value, the magnitude of this component at the next step should be also less than these components at the previous step. And I want this to be true for all steps. So from this condition, I can derive the estimations for the component k, for the component of matrices k. So in order to do that, it's actually a well-known algorithm. So first I have to expand this to Taylor series, and that's a reminder in the Lagrange form and with the mean value theorem. So I denote delta t as tau r. Okay, so that's technically the same condition. And here I used, I think, the triangle inequality. So then I'll denote the absolute value of this deviation as epsilon. Then I can also use triangle inequality and obtain this condition. So then if I'll rewrite it one more time and introduce here epsilon k it's the absolute value of deviation only for the kth component. But if I'll introduce the maximum deviation and the minimum deviation for all components, then I will derive this condition for the components of the matrix K. So they do depend on the integration step, and they do depend on the remainder, right? So, and obviously on values of epsilon. So, and I can actually show that it was shown that the values in this range, in this diapason, I can actually achieve the stable numerical solution. Okay, so I'll continue. Delta here, by the way, is Kronecker delta, but I think it's kind of obvious. Okay, so and then possible applications to Baumgarten stabilization methods that we were researching. So first, we can actually, so as I have said previously, that Baumgarten stabilization method allows us to decrease the deviation from the constraint equations. And we might actually, it will help us if, for example, we have a problem with a singularity point. So, for example, if we have a numerical solution and in some point the solution will blow up because of the singularity, but the analytical solution exists. Well, for example, something like this: square root of x times x dot is equal to, I don't know, 1, for example, or maybe without square, just x dot. So if I'll try to solve it numerically, it's the simplest example. So it will have a singularity. It's if x is equal to 1, but obviously that is just the derivative of x prime squared over 2, right? So technically, so x squared over 2, right? So technically the blow up only occurs at the numerical solution. So the same is happening here. So if you consider these Lagrange equations, it actually connected to the rotations of the rigid body. It's some representation of it. So this part is actually the Lagrangian of the free motion on the three-dimensional sphere. So just a potential energy, and that's just the coordinates of the point mass or the center of gravity. So I'll consider these equations for just denote these equations for this Lagrangian equation. And you can see that for this dynamical equation for gamma, you can see that here's the coefficient tangent beta. But you know that if beta is tending to pi over 2, then unfortunately this term will blow it. It will increase to infinity, right? So if beta is tending to pi over 2, is it approaching to pi over 2? So the idea behind this is, by the way, do you still hear me? Because maybe the connection is lost. No?
We hear it's okay. Sound.
Oh, okay.
So
because I can't see the screen. I can see.
Yeah, because I asked question and I stopped asking questions. Right. So
yeah, maybe because of this.
Okay, it's fine. Please continue.
Okay, so then we introduce some constraints. It can be, of course, the condition that the motion should occur without sleep. So it can be anything. And the idea is, if at algorithm we see that beta is approaching to some delta circle over the singularity point pi over 2, so we stop the numerical integration and we skip this by redefining beta as follows. So we artificially stop the numerical integration and add the deviation by our hands, right? So we just skip the singularity point, and we assume that the stabilization method will help us to get rid of this, to get rid of this error, right? So the equation will, so after, if the algorithm sees that if beta is approaching at the next step is approaching to this this range near the singularity point, so it stops and redefines the difference scheme, define a difference scheme for its velocity as follows. So it's just the artificial break of this result. So it's just the formula for the tangent of sum of two angular coordinates, where we choose delta and epsilon and delta. We choose them. And it turns out that it kind of works, because that's the dependence, as you can see, between this beta in radians. And you can see that is it closer to pi over 2, then we just add it plus delta and it keeps going, right? But the trajectory, you can see that if we turn on the stabilization method, here you have this little instability here, but the value will still decrease and it continues on it's trying to tend to its original real solution. The same is here. The same is here. So it's okay. So it turns out that the stabilization method allows us for some problems to get rid of instability, which we by our own hands have implemented because we want to skip the singularity point. So that's the idea. And we have shown that for some problems it works. Well, another possible application is actually connected to the problem, also analyzed and investigated by some scientists in our department, by Yerugin. So he was investigating in universe dynamical problems, just like Galiulin, Mufamedyanov, and Mufalyanov. And so the idea is actually how can we construct the system of motion equations, which are differential equations, with respect to the given set of constraints. So it can be holonomic constraints, it can be non-holonomic constraints, because holonomic constraints, they can be presented in this form, right? We just take the derivative and that's basically it, right? So this problem is solved a lot of time ago. So by the way, the graduate student from this university, Ramirez, wrote a book which shows the proof that Nambu brackets, the generalized version of Poisson brackets, allows us to construct the solution for this problem, right? So technically, this is kind of solved already. So, but the idea is we want to solve it with respect to the stabilization terms, and we want to show the connection between the stabilization terms and the dissipative function. So that's what we're going to do. So the simplest way, we can use Nambu brackets, we can use this approach, it doesn't really matter. So we just, one more time, we consider that this is a set of algebraic equations with respect to the generalized velocities. And obviously that the rank of this system is less than n. So we must consider the general solution, the fundamental solution, and it will be arbitrary, right? It will be arbitrary, and I'll just redefine the constraints as follows. I just wanted to derive the velocities because it will be much easier, right? So, and I chose these functions such that if I'll put it back here, I will get the true expression. So then I'll turn on the stabilization equation, right? So it's a kinematic equation. That's why I only need the first derivative. So I'll consider this stabilization term, and well, I will just put this equation here and take the first derivative, and I will have this set of equations. So that's technically it, but we have this, it's a stabilization term, and we want actually to check if this set of equations can be reduced to a specific form, or more specific to the Lagrange equation form. So I will just check the sufficient conditions, not necessary conditions, to sufficient conditions. It's called the Helmholtz conditions, or in our case, to generalized Helmholtz conditions. I remind that the just Euler-Lagrange equation checks or makes it possible to the set of equations be reduced to this form, the form of Lagrange equation of the second kind. But if we're talking about generalized conditions, Helmholtz conditions, actually these conditions were derived by Mayer, German mathematician. So these are generalized conditions, and they are actually making possible to derive the equation to this equation, but only with the dissipative term. It has a dissipative term, where d is a Rayleigh function or a dissipative function, where s and d here is a dissipative function. It can be actually a biquadratic form, it doesn't really matter. So anyway, our set of equations must be satisfied by these conditions. So, well, technically the first one and the fourth are quite easy to maintain, right? Because I think they're already right satisfied, so we get rid of them. Let's start with the second, and let's show that, let's denote, for example, that S in that condition is as follows. And if, for example, this tensor is symmetric, then it's actually just DAB. So, but it cannot be symmetric. It doesn't matter. So anyway, we if we put it in that condition, we'll have the following expression, and this expression can be treated as some sort of equation with respect to our stabilization function f, and it's a stabilization function, right? So it's an equation in partial derivatives. It's a linear equation in partial derivatives. So it has, so the idea is we can actually, it has a lot of solutions, right? So we can combine several terms, so they will cancel each other and it will be equal to 0, right? So we can actually try to find a general solution. It's not a big problem. So the idea is actually that we can combine several terms to maintain this condition. So I'll just present you only one possible solution. If, for example, I'll denote this partial derivative as follows, and if I put it here, and if I add this condition and put it here, then it will be equal to 0. So, well, the solution to this, right? The solution to these equations is as follows. And you can see that it's just a linear form of our constraints. So it's a linear form of our constraints. The stabilization function is just, in our case, the linear form of our constraints, and it's a function, right? A well-known function, and these are the coefficients. They can be treated as the coefficients at the quadratic form of the dissipative function, and we have never introduced it, right? So these functions can be chosen by us. It can be chosen by us, and anyway, this solution will be these equations our equations should satisfy all these conditions. And so if I put it to another conditions, we will get these expressions, and I have said that the dissipative function. So we have shown that the stabilization function is does actually depend on the quadratic the parameters of the quadratic form of the dissipative or relay function. So it actually, yeah, it's kind of expected result, because if the deviation from the constraint is decreasing, then we have some dissipative force that decreases our energy, right? So that's the meaning of the dissipative force. Okay, and another possible application. So it helps when we have a system with a lot of variables, and because we have a lot of variables, then the accumulation of errors happen a lot faster. So we do have to use the proper way, the proper stabilization method to achieve the numerical stable solution. And the example of this case is actually the multi-link system. We worked with this with Borisov and they from Smolensk branch of MIE, Moscow Energy University. So he suggested that actually our method can be applied to achieve a stable numerical solution for this model. So he introduced the matrix generalization for any number of links. So, and our goal was to just to obtain to solve the stabilization problem. So that's on the picture. You can see the model of the multi-link system. It has like each link is attached with a hinge. So with the ideal hinge, obviously, right? So and it has several coordinates. It has center of mass somewhere here. It can be anywhere, by the way. So let's consider this model. It can be connected. Doesn't matter to any points, but let's choose that it's connected to the center of this link. And let's suppose that this link is always lying on the surface, and this surface is inclined with an angle alpha. So this model can describe, for example, the motion of an exoskeleton or mobile robot. Okay, so, and that's the Lagrange equation for the Lagrange function for that model. So you can see that it has the kinetic term, right, and the rotational term. And here omega is just this the vector, the angular velocity vector, and g is the moment of inertia. So it's the g here is obviously the acceleration of the free fall. Okay, so and let's consider this Lagrange equation. And so then we want to introduce several constraints. The first is constraint is already considered by us. It's an holonomic constraint. But then by choosing the constraint, the set of constraints, we can actually define the mode of motion. So by choosing the specific set of constraints, we can actually set or define the properties of the motion of the system. And so we actually might use it. We actually might use it, for example, if we want for our model to conserve a stable vertical position, we can use these constraints. So, and if we'll turn on the stabilization method, we can show that if we have these constraints, then the numerical integration will lead us to these graphs. And here we choose delta if for example, we don't want that the deviations from the vertical position, right, pi/2 should not be less than some delta. So these delta are chosen by us. And you can see that the bigger delta, then the bigger deviation will be, right? So that's the graph of the first vertical link, and that's the plots for the second vertical link. Okay, so and the final possible application is for space navigation. It's actually another cooperation with Professor Azimov from the University of Manoa in Hawaii. He said that he suggested that we can use the stabilization methods, but only to implement it to the optimization problem for the first derivatives, for the first integrals. Well, so you do know that the simple systems are described if its mass is not constant, right? It's described with the help of the Michersky equation as follows. Here, F is a reactive force, P here is just the power of the engine, I is the momentum, G is the free fall acceleration, M is just a mass, right? So if I define the state vector as follows, so it has 3 coordinates, positional coordinates, 3 velocities, and a mass, right? So let's consider that our spacecraft is just a point mass. So, and then let's consider its conjugated vector lambda, because now we can state the problem of finding the extrema of this functional. It's a well-known problem for the optimization of the trajectory. So here, this is the Hamiltonian of this expression, and these are just the initial and boundary conditions. And J is just some other extra functional that depends on the finite point. And of course, let's define that our finite point is the mobile, right? So we want to solve this functional, the problem of finding extrema for this functional. And the equation we'll write in the terms of the Pointryagin equations. These equations, by the way, were derived by Loudon, so these are also called Loudon equations. And these are obviously ordinary differential equations, right? So And then if we, for example, we have to consider also transversality conditions because we have mobile ends. So the solution must satisfy to the transversality conditions. And if we have some other constraints, the constraints must satisfy to the condition of the local minima, local maxima, based on situation. So, and if, for example, we introduce the non-zero deviation from our state vector at some points t0, so that's epsilon is our non-zero deviation. And if I introduce first integrals as follows, so what you know what first integral is, right? So if, for example, x dot is equal to x, then g dot must be equal to the g partial derivative with respect to x times x, right, should be equal to 0. So that's technically the Lie derivative with respect to this vector field. So that's by definition the first integral. So, and let's try to assume that the stabilization method will also can also be applied to the first integrals. So these are our well-known stabilization equations, where K is also the matrix with components, can be either constant components or the functional type, doesn't matter. So these are those stabilization terms, and we want to include these terms, and we want to include these equations to our set of Pontryagin equations to get rid of this epsilon. So we want to nullify, to get rid of this initial deviation, if of course the stabilization will work, right? So the first integrals, as I have said, for this problem was derived by Professor Azimov. So he suggested that by stabilization these two integrals we can obtain the stable numerical solution. So, but by the way, the integrals they can form an algebraic structure, but that's not a case in this report. So, and these are the results of the integration. So you can see that in y-axis you have the deviation from the trajectory, and in x-axis you have time, right? So for these each multiple line corresponds to the specific value of epsilon. Epsilon is, as I have introduced to you earlier, the deviation from the initial coordinates, right? So, and when I put it here, so you can see that if epsilon is 0, then the deviation is always 0, right? But if it's non-zero, then the stabilization actually works, and it's actually tending to the stables to its real solution. So that's technically it. That's technically it. And the conclusions are as follows. Time. Oh, yes, I think occupied almost an hour. So it turns out that Baumgartner stabilization method allows us to obtain a numerical solution stable in some relevant problems. So in some problems, it allows us to skip singularities, to bypass singularity points during the numerical integration. And it turns out that it demonstrates the connection between the dissipative function and the constraint stabilization. So these are all the conclusions, and thank you, listeners, for this report. And these are the references if you have some extra questions.
Yes, thank you very much for this very interesting presentation. We have some time for discussion, and I would like to ask you about the structure of the system you consider. I suppose that you need certain structure, like for example, you mentioned Hamiltonian systems. Is it really the class of systems you consider Hamiltonian systems, or it can be also some other systems?
Well, if you're talking about the stabilization method, right? So
of course, yes, about stabilization method, yes.
It can be not, so it can be any differential equations. So the origin of equation does not matter here. So it can be Lagrange equations, Hamiltonian, any equations. So
but ordinary equations, yes.
Or ordinary, yeah, ordinary. Of course, yeah.
With some constraints, because as far as I understand, you impose this stabilization function enters the equation for constraints, right?
Yeah. And the last problem for first integrals, if
right.
we know them.
And what about the time interval? So you have this numerical, well, an estimate of the of this approximation of the exact solution and numerical solution. Does it depend on the time interval, or you
Yeah, of course, yes. It was not included. Yeah. I did not include it in the work. I can show you here, but we show that, for example, if x with tilde, or I don't know, x prime is a numerical solution and x is a real solution, so that's the deviation, and the deviation is actually proportional to e to the power of t plus some stabilization. I might not remember it exactly, plus some stabilization terms, where t is the interval of integration. So the bigger interval, so the deviation will blow up exponentially.
Yes, but
so okay.
Yes, when you write this e to the power t plus stabilization, well, stabilization in fact should be negative in this representation.
Of course. Yeah, right.
Yes. Okay. Right. How it can be related with Lyapunov stability, Lyapunov exponentials? I mean, this stabilization method. Is there some kind of connection behind that, or you don't know?
Well, it has some connection, because when we choose this function f, we should demand that this function must stable in Lyapunov sense. So it should be not asymptotically stable by Lyapunov sense, but for x, just our x. So technically, this stabilization works if, for example, our solution is not stable. Well, so it can be anything.
Could you repeat? Is not stable or stable?
It cannot be stable. It can be anything.
Well, okay. You also mentioned these problems with singularity. I think that this is particularly interesting and important, and really not trivial result about this avoiding the singularity. How general is this result about singularities? For example, if you have a problem with obstacle or something like that, can you what kind of singularities, what kind of problems you can consider from this point of view?
Well, first, we consider the problem when I have a degenerative Hessian matrix. If, for example, Hessian matrix is as follows. And if, for example, at some point t0, the determinant of this matrix is equal to 0, then it's a singularity. And well, for that singularity, I have already showed you, because technically that Lagrangian came from the Lagrange function of the Euler equation, and you can see that that is a singular case in Euler equations for rotation of the rigid body. So it technically came from here. So it technically should work, but I have only checked it at several examples. So I can't tell for sure whether it works for the general case.
Well, thank you for these answers. Are there other questions from the listeners? Well, if no other questions, then thank you again for this interesting presentation.
Okay, thank you. Thank you for having me.
Yes, and thanks also to all listeners. It's our last seminar in this year. We'll start again in January. So I wish everybody good holidays and
Happy New Year,
next
right?
New Year, right? Yes. Thanks to everybody, and bye now.
Merry Christmas, yeah. Thank you.
All right.